So, hi all, so good evening. So today in this session, without wasting the time, we'll start into understanding the BMS side, like the sensing, the features, the estimations. Okay, we'll just try to see the basics of it, like just an overview part of it. Okay, like not in depth of like how we can build the logic for these like if you take any uh, features or like estimations. Okay, yeah. So let me jump to the agenda. So here like first we'll start with BMS sensing. Under the BMS sensing, like we'll see like what all parameters of the cell. Okay, whenever we talk about the BMS, it is like battery management system. Okay, so when we talk about the battery as a whole, and if you consider a part of it, it is a cell. So what all the parameters we need to monitor when we talk about the battery? Like one is with respect to the voltage of the battery. Okay, and one with respect to the temperature and the current. So these three parameters like has to be operated within like a threshold, you can say. So if you take up a lithium based cell, like we usually define in a general that the voltage will be like 4.2 has a over voltage and 2.8 has like under voltage. Again, within that, like NMC and LFP, like they are having different uh, cutoff and cutoff, over voltage cutoff and under voltage cutoff values. So we'll discuss those points. So in general, if you take this one, these are like limits. Okay. In the same way, there is a temperature, operating temperature, and also for the current operation. Okay, like you can say it as like operating current values. Within that, you can like discharge, charge. Okay, yeah, and then like we'll discuss about uh, the battery protection features. We'll try to touch like possible battery protection, which are most of them are like software like developed, like under voltage conduction. Again, in that we have different levels, level one, level two. We'll try to like understand those, and then we'll try to touch the topology of the BMS and the BMS estimations. Uh, we'll try to see different types of SOC estimations methods. Okay, yeah. So when I talk about voltage sensing, okay. So when we talk about like vehicle, okay. So let's take like a two-wheeler, like a scooty segment. Most of the scooty segment vehicle having like 48 as a nominal voltage of their battery. So almost based on different cells, like 13 to 14 cells will come in series connection. Okay. So like now not to worry about the parallel. Okay. So almost like let's assume that 14 cells are in series. So each stack of the voltage, like all the 14 stack voltage has to be monitored. Okay. So this is for the vehicle level. Okay. When you take up any small devices which run by a single cell, for example, if you take your telephone or like phone, you can say smartphone, it runs by a single battery pouch cell. Okay. Like so for this battery also has a BMS. where it is going to collect the parameters that voltage, current, and the temperature in order to monitor. Okay. So how it's going to measure? So basically, when we talk about the voltage, like you just trying to like measure the potential difference. Okay. So that is how you are going to measure the voltage. Like uh, with the technology, you can say that like you can use the ADC converter, which is a basic way. When we talk about the single cell, okay, then let's say like for 14 cells in series, or like 28 cells in series. So then the different type of technology we need to use. Okay. So then there is a chipset technology, like for high voltage battery architecture. So where we can measure like more than single cell. Okay. So I have put some like examples over here under the TIs, BQ series, and the LT 680 X series technologies. And even on the NXP, there are there MC37. Okay. This is under NXP. So these are some uh, AFE. I can call them as a AFE, analog front end. So these chipset like are organized to measure the cells. Okay. So if I try to like take up a microcontroller over here and I want to measure the voltage of the cell, so you can directly give one positive to the analog and the negative to the ground. Okay. When you talk about like multiple cells, like you need to measure, then you need to go for like divider architecture, but with the help of RC circuit, it's become complex. So that wise, like all the voltage divider architecture with RC circuit for the filtering, it all integrated within this AFE chip. Okay. So then if this is microcontroller, then this will be your AFE, that is analog front end. So these chip will be connect to the multiple cells. Okay. Yeah. So you can like connect a number of cells, and this AFE, that is analog front end, will be communicating to the microcontroller through some COM. Okay, like some communication protocol. It might be like SPI, like anything. Okay, or like CAN. I don't think CAN. Like most of the time SPI. Yeah, because this AFE will be only acts as a transmitter. This will act as a master. Yeah. So in high like multi like series, like let's say like high voltage battery, like these kind of technology will be used to measure the voltage. And then about the current sensing, like we divide that shunt resistor base and the Hall effect base. Uh, so again, it depends like whether the current like either the resistor or the Hall effect based, whether it is going to, let's say like if it is IC, it is going to sit on the controller that is on the BMS or not, or it will be externally held. That it depends on uh, how much the current you are trying to draw. Okay. For example, if you are taking a shunt resistor base resistor, shunt resistor based current sensor. So this will be your like controller. Okay. So let's assume this is your like controller, and somewhere here will be your like resistor. So positive of the battery and the negative of the battery will be connecting, and 2 points you will be like taking like V sense and V sense positive and sorry I sense positive and I minus I sense negative. Okay. So with that, like whenever you are trying to like draw the current, you are going to see the difference of the resistance. Based on that, you are going to like drop the current, or like derive the current values. So this can be like externally held. Okay. This can be held the externally. Uh, so you don't need to like include into the microcontroller, so that you can like even with a high current ratings can be measured. Okay. Yeah. So right now, like you just consider current sensor has shunt resistor based and Hall effect based. And then we talk about like temperature sensing. So right now, like one with the thermocouple, and in most of the EV thing, like we are going to use this thermistor based, like NTC you can say. So one with cost, which is very less, and one with like flexibility. Okay. So as per our like standards, AIS 156. Okay. So minimum of like 4 NTC or like temperature sensors has to be placed within the whole battery pack. Okay. So it has to like take all the data like, and later it depends on us like how we are going to make all the 4 sensors data. Either we are going to make average of it, or like take individual like has a max of 4 or like min of 4. Okay, based on that we'll plan it. Okay, right now like we need to place 4 NTC as per the AS 156 standard. Yeah. So these working principle you can just like either for the thermocouple or the thermistor, you can just check in the Google. Okay. Yeah. Then like the need of parameter sensing. So like as I said, when I talk about like cell, we need to we only consider like 3 values, that is current, voltage, temperature, as the inputs to your BMS. These inputs we are going to get it from the battery itself. Okay. So with these parameters only, we do all these protection feature developments. Like okay, and like so if you control them, then you are like protecting the battery itself. Okay, and then with the help of these only, we can go for parameter estimation. So those can be like SOH, SOC, and cell balance is the other term. Okay, and SOE, that is state of energy. Yeah. So okay, this is about like sensing part. Now like I'll discuss about the topology. So when we talk about like BMS topology, uh, we divide like BMS into like different architectures. Like one, I mentioned it as a centralized BMS architecture. There are modular and single cell. Okay, even like individual cell have a BMS. Okay, we'll discuss that later. So why this topology has been derived? Okay, so let me explain that one. So when I talk about BMS, okay, like for example, like 48-volt architecture vehicle. So as I said, at least you need to have 13 to 14 cells in series in order to achieve this value. Okay, 13 to 14 cells of nominal voltage. Yeah. So the microcontroller, we have limitations in terms of analog pins in order to like read all the voltage values of the cell. Okay. And then if you talk about the EFE, that is the like that's why like we are using EFE, that is analog front end, where it has like analog inputs. Okay. So even when we talk about the analog inputs, it also has some limitations, like in terms of numbers. Okay. So that's why like they have derived uh, different architectures like centralized. Okay. Yeah, we'll take the doubts later. Centralized and modular. Okay. So for example, like if you take up like 14 cells in series, or like 48-volt or like 60-volt battery, we usually like have a single BMS itself. There is no like master and slave uh, or like anything. Okay. So when we talk about like modular architecture, there is a concept of like master and slave. Usually this comes in very heavy duty vehicles. Like if you take up like lorries, buses, like they have like 600 to like 700 voltage architecture, right? So there comes like the number of BMSs, like instead of like I saying BMS, the EFCs. Okay, you can see here with this picture. So if this is one battery architecture, this one and this one. So all these like let's say within this battery module, let's assume that they are in 13 in series, 13s, and this is 13s. Okay, I'm just taking random like number here. Yeah. Okay. So here for individual like module, for individual module, like each AFA has been integrated. Okay. So this each module may have connected in series. So at the total, it may like let's say like 48 plus 48 plus 48. Okay. So whatever the voltage we get, right, that will be out like total voltage if you connect them whole module in series. Okay. So this each AFE, it means like this BMS, you can say it as slave BMS, is for the module level. Okay. So what exactly this slave BMS does? It takes only the voltage information, like voltage of all the cells, and if possible, the temperature also. And in the advanced EFEs, they have the balancing circuit also. Again, that balancing circuit has to be derived from the logic has to be derived. Like whenever the balancing has to start, or like when the cells has to engage with the resistors, that has to be derived from the logic has to be derived from the microcontroller. Okay. So whatever the information it takes, okay, like it will send it to the microcontroller. So let's say you want to like cut off the battery when there is a over voltage or like under voltage, and if you are trying to draw like more current, or if the temperature is high. Okay, then you want to make the decision whether to supply the current or not, or like whether to discharge or discharge. So that logic will sit in the microcontroller. Okay, and even the SOC estimations, SOH, like SOC, sorry, SOE. So all these like estimations algorithm will sit over here. So for these like SOC, SOH, so SOE it requires based on different method. If you are like going for Coulomb counting, you require current. So where you are getting from the current sensor. So if you are going for voltage based, so you need the voltage data where you are getting from this AF itself. So from these you will get the data, and based on that you will do the estimations over in the uh, master BMS. Okay. Yeah. So usually when I talk about like centralized BMS, it is used in a single set, in a small vehicle applications. This is BMS for the heavy vehicle, and then okay, one is with the modular BMS architecture, and then the distributed BMS architecture. So when you take up like again in the heavy duty vehicles, like uh, in one of the example I can take like Tata Ace Electric, like yeah, they have one individual battery capacity of like almost 150 Ah, maybe like 180 Ah. Okay, I don't remember. So, but the voltage will remain like uh, 3.7 as a nominal. Okay, so these like when we talk about like high capacity battery, then it is possible to like allow individual uh, a monitoring chip, okay, to the cell for the cell level BMS, you can say. What exactly it does, like again, it measures the cell voltage, like whatever the uh, modular BMS that AFE was doing, right? Temperature, voltage. So it carries the information uh, through some communication protocol. It will pass through the controller, and finally it controls. The same thing. Yeah. So when we talk about like topology, we divide one with centralized and modular. If you have like modular type of battery packs, obviously you are going to deal with the master and slave BMS. So again, in the modular, there is a series type modular and the parallel type. Right now in the market, like for the two-wheeler, all are concentrating on the series type itself because of they are not concentrating much on the parallel type because of like lot of difficulties in terms of bringing into the practice. Okay, yeah, and then the distributed, yeah. So where there is a individual cell, there is a single cell BMS. Yeah. So this is about like topology. Then like I'll try to touch some. You can just make a note, or like you can take a screenshot of these things. Uh, yeah, I'll try to explain one uh, here. Let's take like over voltage protections. So I have listed like something about like 25 protection features. So over voltage protection, 1, 2, 3. It means like level 1, level 2, level 3. Same with respect to the under voltage, level 1, level 2, level 3. And even for the pack level, level 1, level 2, level 3, under voltage and voltage sensor fault, battery over temperature, level 1, level 2, level 3. under temperature, battery temperature sensor fault, okay, and charge over current, level 1, level 2, level 3, and discharge over current, okay, insulation alarm, string voltage imbalance, IC temperature protection. Yeah. So I'll just try to like explain like what is level 1, level 2, level 3. Okay. So you can, it is same for all other thing also. So when you take up the over voltage protection, let's say like one cell, you have built the logic, assuming that you have built the logic. So for this over voltage value is like 4.2, okay, which is given in the like data sheet, and voltage is something like 2.5. Okay. So when you like bring up this over voltage condition warning one, so in the first you have configured the value like 4.2. Let's, instead of like 4.2, I will take 4.15. So this value, like assume that I have kept it as a over voltage protection one value, OVP. Okay, one. So whenever you are charging the battery, when the cell out of like 14 cells in series, if any one cell, the max voltage cell reaches 4.15 has a voltage, it will start giving the warning. Okay, you can just see here, it's just giving the warning that is over voltage. Yeah, that warning for how many seconds it is trying to give, that you can like mention. Okay, that it depends. Okay, deriving these values and up to what monitoring time, that it has to be derived through some testing of the battery. Okay, not we can't just put some random values. Yeah, so for our case we'll just mention 3 seconds. So as the cell reaches 4.15, and if it is observed for 3 seconds continuously, then this like protection start triggering. Okay, yeah, then at the second over voltage protection, that is like over voltage protection 2. So I will keep the value as like 4.17. I'm just taking random values right now. OVP 1, 2, sorry. Yeah. So when the voltage, despite of this warning, if it reaches 4.17, then it is going to affect the performance. Means you are charging the battery. First you will reach 4.15. You will get the warning, but no effect on any charging or discharging side. Sorry, on charging side. So when it reaches 4.15, you are going to reduce uh, the charging current. Okay. Yeah. So you might be reduced to like 50% or like 25%. So you are going to reduce the charging thing. And the third, like over voltage protection 3. So let's say like I have kept 4.22 as a value. So even after reducing, it will be charging, but very slow. So again, if it reaches like 4.22, let's say, then it will go trip condition, like complete cutoff. Yeah. So this is how like this work, this protection like alarms work like at different levels. So the same thing will be for under voltage, like 1, 2, 3, and even for pack and pack under voltage. Okay. Yeah. So then like I will talk about this voltage sensor fault. So because this remains same for like all the same one. Okay. So voltage sensor fault, like when you take up individual, like when you talk about the BMS, you will measure the cell level voltage, cell 1, cell 2, cell 3, and pack voltage. So if the difference of both, for example, 14 cells voltage, you just uh, take a summation of it, something you will get like 47. I'm just taking it. And the pack voltage is something like 47.5. This will be like 0.2. So if both the difference of the pack voltage and the summation of individual voltage, if it is like greater than some threshold, then the voltage sensor fault. This is going to be triggered and it is going to reduce the performance or trip condition, because uh, if any one individual, like let's say if when you trying to measure the individual cell voltage, if one cell is not giving the proper data, it's going to affect at the summation value, right? So then at the overall, if it is having a larger difference, then it is difficult to consider. That's why it's going to trip condition or the reduce the performance. Okay. Yeah. So then like if I talk about the battery over temperature, and battery over temperature 1, 2, and 3, then like battery over temperature. So again, it will be defined with the different levels. So the first level like can be kept as like, I'm just taking random example like 45, 50, 55. Okay. So this can be like level 1, level 2, level 3. So again, in the first, as it breaches this temperature, it gives the warning. And if it reaches the more than 50 degree, it affecting the performance. Means let's say like you are discharging the battery, you are driving the vehicle. So if the battery of the temperature reaches the level 2, okay, don't worry about this number, I'm just taking random value. So if it reaches the level 2, like alarm 2, it affects the performance. The performance suddenly drops. So like let's assume that your vehicle has the ability of like reaching 0 to 60 within like 4 seconds. It's going to reduce. Okay. Like now it may take like 0 to 8 seconds. So in this way, like your acceleration and everything, it is going to reduce. Yeah. At the end, we can like discuss once we finish it. And yeah. So the same with respect to the level 3, it undergoes the trip condition. So next, like uh, the charge over current, uh, discharge over current. Okay. So this is now like in the previous like features we went through like voltage, protection, that is under voltage, over voltage, different cells, like levels, and for cell level and the pack level, and also the temperature. Now like over current, that is the current parameter. So when you're trying to draw like more current, either in charge or discharge, okay, uh, you are going to like undergo the same scenarios here. If the first level, like it's a warning, and the second level, it affects the performance, and the third level is the trip condition. So why these like alarms, okay, like how they have derived. Okay, so these like in order to bring the proper criticality within the BMS. Okay, so these like level of warnings and affecting the parameters like they have been introduced uh, like for all these parameters. So if just has a customer point of view, if suddenly at the level one, if it undergoes the cutoff, it's not good, right? Like it should you should like get at least a warning. That is as a one part. Uh, and these features like can be modified according to the OEM needs. Okay, they are not like fixed. It depends on like how the OEM comes with different feature developments for the protections. Okay, yeah. So as I was mentioning that like for over voltage, like 4.15 has a like level 1 protection value, 4.17, 4.2. It depends on how you set the value. Like these will be derived from through the testing itself. Okay, so you need to do the testing the cell at different conditions and come up with the data. So it depends on like OEMs itself. Like they are going to uh, make the decision, or like battery pack manufacturers. Okay, yeah. The same for even current also, and also for temperature values. Yeah. And even like if there is a voltage difference among the strings. So this is like one series, like second series, third series of the cells. So if the stack voltage, like if there is much difference between each stack voltage series, then it won't undergo like charge or discharge. It reduce the performance or like undergo the trip condition. Okay, yeah. So even the insulation alarm that if there is any current pass in the chassis of your vehicle, that is monitoring also, it is kept insulation monitoring and short circuit protection, and even IC temperature protection level 1, level 2, level 3. So even your ICs, like as I said, AFEs, microcontroller chips, and other ICs, even the FET, okay, that is your MOSFETs, like they will also get heated up when they are draining the current. Okay, so because of the dissipation of the heat, so those like also have some limitations in terms of temperature. Okay, when they reaches their max value, still the BMS like will stop like working, like a trip condition. Okay, yeah. So all these like uh, features are developed for the battery protection and the BM like for the vehicle level. Okay, and even the components at the BMS level. Yeah. So next, like we'll talk about like parameter estimation. Like I'll just quickly go through this one. One with like state of charge. Uh, it's a measurement of amount of energy like available at the battery pack at a specific point of time. Okay. So these again divided into like different methods to measure the state of charge. One with like voltage based and Coulomb counting. These are like basics. Even in like present market, they are using like voltage based and Coulomb counting or hybrid. Hybrid means like combination of both. Yeah. So and then there is a EKF based Kalman filter, okay, which is very like complex. Like let's not worry about right now. Yeah. So when I talk about like voltage based current, sorry, voltage based SOC estimation, you should have a data that OCV and then like the resistance of your cells in order to derive this approach. Okay, so you are going to map. Yeah. So if you see this look, something a block I have kept, this is we call it as lookup table from the Simulink. Okay, so input will be your like voltage value, which you are getting it from the sensor of your battery, and output will be your SOC. So completely you are measuring your value, SOC value based on your voltage data of your battery. Let's say like 4.15 is your 100%. I'm just assuming 3.7 is like 50%, 3.3 is like 25%, 2.8 is your 0%. Okay. Yeah. So this works when there is a static discharge and charge conditions. When there is a dynamic, uh, it doesn't give much accurate data. Okay. Yeah. And when you apply like heavy load, then there is a lot of voltage drop. So you have to consider the correction factor when you are trying to implement the voltage base. Then we talk about like uh, Coulomb counting base. So we use this equation in order to like calculate the SOC. This will be like your previous SOC, and you are integrating the current with respect to time, and finally dividing it with the battery capacity. So here, like let's assume that your battery SOC is something about like you are starting it from initial. Let's assume that it's 100. So your initial SOC is 100. So you are replacing the whole term with 100. For first second, you're trying to draw some current like 3 amps. Okay. Let's assume that cell is of 3 Ah. So you're trying to draw 1 C current for first second. So 100 like minus 0 to 1 current can be something like 3 amps. C bat is nothing but 3H, right? 3 into 3600, yeah, into dt. So if you, yeah, let me, yeah. So if you like try to simplify this thing and assuming that you will get some value, like just random value, 0.1, okay, yeah. And if you subtract from the 100 minus 0.1, so it will be 99.9. Okay. Yeah. So this will be the SOC at time t, that is t equal to 1. So if the time 2 at the second you're trying to draw 6 amps. Okay. Now you replace your like 100 amps, it will be replaced by your updated SOC, that is 99.99 minus and the same repetition. So in this way, like it will estimate the SOC. So, but when you talk about the reality, like let's assume that if your battery is starting itself is from 60% SOC, how you are going to initiate here? So this is the initiator value. Okay, either this has to be fed through initially with OCV, that is voltage based SOC estimation, that that initial value has to be fed and then further taken into calculation. That how it works in the reality. Okay. Yeah. And then like EKF based. Okay. This is one of the approach. Like it's very complex. You need lot of data. You need battery data, whichever the cell you are going to use. So you need to like understand the OC value at the different SOC and temperature conditions. And the same with respect to the R0, R1, R2, C1, C2 in order to build the RC circuit. And then like with that, you will estimate the terminal voltage. Okay. So on one end, you will be measuring your SOC like terminal voltage of your battery or the cell through theoretical method, that is with the help of cell model, the digital twin. On the other hand, you will be getting the sensor data. Like you will be measuring the live voltage of the cell and the current, whether it is drawing or discharging or charging. So based on that, you will be measuring the current. And with that, you will be measuring the like SOC also. Okay. The state variables. Yeah. So with this, like we introduce this Kalman filter approach, where to which uh, part either theoretical base has to be given more weightage or sensor based estimation, that is measurement, has to be given with the more weightage. That can be decided again with the Kalman gain. Okay. So based on that estimate, we'll come with the conclusion. Okay. So every time like it will predict and it will be updated. Yeah. So I know like it's very difficult to understand. Like we'll try to have like a separate session on this part itself. Okay. I think like I have covered some pretty much concepts here.